We can get rid of one other term.
Mass?
Oh, well, okay. We have a factor, MO can be canceled out. It is in every term. But we can still get rid of a term.
Okay.
Is it the radius initial?
If radius initial is 0, what does that fraction become?
0.
No.
Wait, no, sorry, whatever the.
You're dividing by 0?
It's not possible.
Breaking the law.
Yeah.
Yeah, that R initial, again, those R's are center to center distance. What is the initial R?
The radius of the planet?
Yes. So this is the radius of the Earth, X. I'll make it a capital R, just so it looks less like a variable.
If it's center to center, wouldn't it also include the radius of the object, technically?
It would. I am assuming that the object is small enough that we don't care.
Okay.
But yes, you are absolutely right. If we had the moon on the surface of the Earth and we were launching the moon, then yes, I think, actually even then, I'd probably take it into account. Well, since we're trying to find VI and nothing here is 0, it does pretty much narrow down what we can get rid of. The question is, why can we get rid of this?
Is it because V final becomes 0 when it? No, our V final would, it wouldn't, yeah, it would stop at some point.
So close.
So we're still in the gravitational field. Once
Right.
it hits that turning point, it's gonna be 0. Velocity is gonna be 0.
Where does it hit the turning point? Turning point implies it's going to stop and then come back.
Yeah. When the gravity is equal to when its velocity
Does that have something to do with the black hole?
Not the black hole yet. We have to do escape speed first.
yeah.
As soon as it's launched, it starts slowing down. It will never stop.
Okay.
But what do you know about the speed?
It can get to 0. No, it can go negative, can it?
Speed won't.
Does it just become so close to 0 that it's essentially 0?
That is the key.
Okay.
It's never quite hit 0. It's still moving out there, but it's getting slower and slower and slower. It will get closer and closer to 0. So we get rid of this term because the final speed is approximately 0 meters per second.
Sort of like our fraction on the right there, where it just gets infinitesimally small.
Yeah.
Okay.
So what we are left with here is 1/2 V initial squared is equal to big G, mass of the planet, over the radius of the planet. So my initial speed is the square root of 2g mass of x over rx. So if we take the Earth, the escape speed for Earth is the square root of 2 times 6.67 times 10 to the negative 11th. Mass of the Earth, 5.98 times 10 to the 24th. And the radius of the planet, 6.38 times 10 to the 6th. Yeah.
Where did you get those values with the scientific notation, like 6.67?
That's the gravitational constant. That's a set number.
Okay.
That's the mass of the Earth I happen to remember, and the radius of the Earth, which I happen to remember. For those not working on the calculator, what will the units be in the end?
What are we finding speed?
Yep.
In meters per second.
Okay. Lisa?
Yeah, so up top, what is the UG mean? Like, is that like,
This?
yeah,
Gravitational potential energy.
okay, and what is the FG?
That's a subscript G, that is the gravitational force.
Okay,
You said the 5.98, that is the mass of the Earth? Or,
Say it again?
you said 5.98 times 10 to the 24th, that's the mass of the Earth?
Yes, in kilograms.
Okay.
That's kilograms. This is Newton meter squared, or kilogram squared, and this is meters.
Did anyone else get about 1.12 10 to the 7th?
Yeah, I got 11,181 time, I'm sorry, 11,181.966 meters per second, but it's basically the same
You
notation.
did square root at the end?
Yeah, well, let's
You
do
got-
that.
you
You
got-
said 1.1 times 10 to the 7th.
Yeah,
That's way too high.
it is. It's something wrong. Maybe one of my exponents is wrong.
Do you do negative 11 here?
Yep. 24 on the other.
Yep, that's 24.
Oh, I wrote the exponent in the bottom of that.
Oh.
Is that 2 to the 8?
I remembered somewhere a little over 11,000 meters a second.
Yeah.
So if I watch something from the surface of the Earth, it would, that's how fast it needs to go never to return, assuming it doesn't hit anything. So I probably have to launch it from when air resistance is close to 0.
Okay.
So, in theory, I give you the mass of the planet and the size of the planet. So if I give you mass m sub x and r sub x, mass of the planet and the radius of the planet, you should be able to calculate the escape speed.
Yeah.
However,
Black holes are different.
there is a maximum speed. I can only get something up to the speed of light, or close enough to it.
Black holes suck in light, don't they?
Light doesn't escape, it's better wording.
Okay.
If the sun suddenly became a black hole, it's not like the Earth suddenly goes spiraling in towards it.
Yeah, okay.
So if we are at that maximum speed, the question, why don't we assume that we know the mass? Let's figure out what that radius is. What does the radius need to be in order for, let's just say the Earth, for the Earth to be a black hole? So I'm going to start with, in essence, this formula right here and solve for Rx. So radius of, I'll put black hole, is equal to 2 big G mass of the planet, or mass of black hole, divided by speed of light squared. Plugging in the maximum speed. In other words, traveling at that speed, you're right at the border between what can escape and what cannot. So this is 2 times, let's take the Earth, 6.67 times 10 to the negative 11th, times mass of the Earth, 5.98 times 10 to the 24th, divided by 3 times 10 to the 8th squared. There is an exact value for the speed of light, but this is good enough for what we're doing here. It's 2.99 something times 10 to the 8th.
It's, well, 0.00886
Units?
meters, no. Yeah, meters.
So it's a little under 9 millimeters. So if somehow we took the entire mass of the Earth and could shrink it down so that the diameter of the Earth is roughly between the size of my 2 fingernails there, escape speed would be at the speed of light. This radius here is known as the Schwarzschild radius. Schwarzschild, or probably closer to the correct pronunciation, Schwarzschild, was a physicist, ended up not surviving his injuries from World War I. He got caught in a mustard gas attack. While he was recuperating in the hospital, he decided to do physics. Because what else do you do?
As one does.
Pardon?
I said as one does.
Oh, as one does, yeah. And he came out with two very influential papers. Einstein, so World War, back up a little bit. Einstein comes out with the idea of general relativity in 1905, comes out with the math, or combines the math with it, displays the math, however you want to word that, in 1915. And so this is just a couple years after that, World War I. Yeah. So, you know, at least he gets some credit, which was nice. But at that point, not many people really understood general relativity. Now, the interesting thing is that what I used here was what's known as semi-classical physics. The fact that there is a maximum speed is part of special relativity, that is known as semi-classical physics there. The rest of it is classical physics. But we get the exact same formula using semi-classical physics as you do using the more advanced general relativity. There's a much more complicated derivation of it.
So what you're saying is the radius of a black hole is only 9 millimeters?
If the Earth became a black hole.
If the Earth, okay.
So, if the Sun became a black hole, then this number here changes to 2 times 10 to the 30th. So that's roughly 10 to the 6th and then a third. So somewhere around 3 kilometers.
Okay, question. Since the radius of the Earth is much bigger than 0.00886 meters,
Yep.
The escape speed is higher, is bigger than the speed of light.
No, smaller, because the radius is bigger. As R gets bigger, the speed gets smaller.
Okay, gotcha.
So if the Sun shrunk down so that the radius was basically here to Peters Creek, or maybe Peters Creek to Haines Mall, if the Sun shrunk down to that size, that our Sun would be a black hole.
When I plugged in that number, I got 6,670.
This one?
Yeah.
6,000.
And I got the same number we had before, I just swapped out this number, so I don't know what
I was thinking it was about half that, but could be my memory. Still, 7 kilometers, not particularly big.
What's that BH mean?
Black hole. The radius of a black hole. Now, our Sun is not expected to become a black hole. That there's two major things going on in stars according to our current theories. Is you have, as the fusion reaction is going on, energy is in forms of radiation, is trying to get out. So we get this radiation pressure outwards. There's this gravitational pull inwards. When the radiation pressure, if the radiation pressure is less than the gravitational pull, that it will start to collapse in on itself. That's how you they shrink. Now, if they collapse on themselves quickly enough, you'll generate enough heat for it to explode, and therefore you get novas and supernovas. If it's even larger, it might collapse to the point where it might explode, but it won't go anywhere, so basically it stays there. You potentially get a neutron star or black holes if it's large enough mass. Our Sun is not massive enough. It is expected that the radiation pressure will exceed the gravitational pull, and our Sun will start to expand. Some will claim that the Sun will eventually burn up the Earth. What makes more sense, what I've heard elsewhere and what makes more sense to me, is that as the gravitational pull from the Sun, because every time you lose radiation, you lose mass. So as the sun loses mass, the gravitational pull on the Earth will lessen and the Earth will move farther out. So eventually the sun will be here, but the Earth will not be. It'll be farther out. Now, humans are not expected to be around at that point, but it is based upon theories.
Those that are around will be very cold.
Anything around, yes, it will be quite cold. Because as the sun loses, because once it uses up all the helium, all the hydrogen, then it's going to go to helium and try to fuse helium, but it doesn't quite produce as much energy as two hydrogens slamming together.
Could humans or whatever intelligent life may be around at that point theoretically move to a closer planet if it had conditions viable for living?
Yeah, potentially.
Only in physics class do we have these kind of conversations.
I think they were trying to say Mars, but the only reason they did is because there's like ice under the surface, but it's so small that it wouldn't be enough to sustain anybody for long enough period for them to colonize.
Yeah, probably not. There's a what if about what if all the water from our oceans ended up on Mars. Somehow there's a tap and our oceans drained and water showed up there. And I forget what the number was, but he talks about how quickly the water would evaporate off of Mars.
Yeah, there's no atmosphere, so the radiation from the sun just hits the surface of the planet.
Mars, you're saying Mars has no atmosphere?
It's minimal atmosphere. So
More than our moon.
so more of the radiation from the sun is just hitting the surface of the planet.
Yeah, so far away. Ultimately, we would have to colonize someplace else and try to figure that part out.
I heard that, the one that's closest to the size of Earth would be Venus, but that's also like the most extreme planet in our solar system.
I'm assuming that by the time we get to the point where we can move to Venus, we figured out global warming and somehow figured out how to deal with the acidic atmosphere.
I don't think that Venus would work out because it's not even able to stand on it. It's just a bunch of gas. So you're.
No, I thought Venus did have a solid floor that you don't get to the liquid planets until you get to Jupiter.
Yeah, but
the reason we couldn't survive on Venus is because we'd get destroyed by the pressure and melted. Subsequently dissolved or vaporized. It's like 800 degrees there.
But by the time we'd be talking about moving there, it would be much further away from the sun, so it wouldn't be nearly as hot.
Well, it's hot because of greenhouse gases.
Yeah, we are irrelevant in this. But
I'm pretty sure it is the greenhouse gases which keep it hot.
so the atmosphere wouldn't change.
It's got 10 times the atmosphere of Earth, but it's 98% carbon dioxide.
Oh.
So it's 800 degrees Celsius on Venus.
Sounds reasonable.
And perhaps by
The
then,
CO2 doesn't sound.
the Earth is doing the same thing. It's doing what we do is what we do. And there's the environmental pitch. See you Wednesday. I am planning to have you do a lab. I just need to make sure that you have access to it.
is there a pre-lab for it?
I think so. I'm trying to remember.
Okay. If
Oh, yes. You get to shoot stuff on Wednesday. Woo! All right, let me stop this first. I'll come back.